Hello everyone, let's analyze. So today we're going to talk about higher order derivatives of multidimensional functions. Second derivative, third derivative, fourth derivative, and we're going to talk about it in the context of the Taylor expansion. So before we get into higher order derivatives and Taylor expansion for multidimensional functions, let's review what it is for real valued functions of real numbers. So let's consider the function e to the x. The 0th order Taylor polynomial for e to the x is of course a constant because the 0th order polynomial is a constant. And if I choose my expansion point to be 0, I just get the constant 1, which is of course f of 0. The first order Taylor polynomial is just the tangent line. It's the first order polynomial that matches f at 0 and also matches the derivative of f at 0. And the second order Taylor polynomial is the second order polynomial that matches f at 0, matches the derivative of f at 0, and also matches the second derivative of f at 0. The third order Taylor polynomial, of course, matches f and the first three derivatives at 0. And of course, the idea holds for the fourth order, the fifth order, the sixth, the seventh, the eighth, the ninth, and of course we could keep going so long as the differentiability of my function allows me to keep going. Now we probably already know that e to the x is infinitely differentiable because its derivative is itself, and that the Taylor series in this case converges because e to the x is analytic. But essentially what we're doing is we're recreating the function by capturing the function value at a single point, the rate of change at a single point, and then the rate of change of that rate of change, and then the rate of change of that rate of change, and so on and forever. But here's another key point that we need to pay attention to. Let's rewrite this Taylor polynomial in a different way. This is a function of real numbers to real numbers. So every term in my Taylor expansion is a real number. As we've discussed before, the first derivative evaluated at 0 is a number. And of course, a number is equivalent to a linear mapping from R to R. For every linear mapping R to R, there's a number, specifically the slope, associated with it, and vice versa. Now, the second derivative, notice, multiplies x squared, or x times x. The reason I'm writing it this way is because I want to think about what that means. This is a linear operator, and a linear operator in a vector space, a finite dimensional vector space, can be represented as a matrix. So we understand how this might be adapted to functions of Rm to Rn because we've discussed this already. But the second derivative has to multiply two elements from the domain of f. Again, here the domain is just real numbers, and x times x is a well-defined operation. So is the second derivative at 0 times x times x. And of course, the second derivative at 0 is a number. And this number is going to scale x times x. But if my function were operating on m-dimensional vectors, then I will need something that behaves like this, where I could take the product of my derivative, a vector and a vector. And for my third derivative, again, if x were a vector, I will need something that, when I take the third derivative at 0, it can operate on a vector x, and a vector x in a way that feels like multiplication. So what does that look like? How do we do that? And of course, again, the key idea is that these derivatives, for example, the kth derivative somehow has to operate on a k product. So, question, if the first derivative at a point x naught in Rm, and now we're thinking of functions that map vectors in Rm to vectors in Rn. So if the first derivative is a linear mapping from Rm to Rn, which we know from our discussions is equivalent to a matrix in Rn by M, of course given a Joseph basis, then what form does the second derivative take? What about the third derivative? The kth derivative, right? And of course from our illustration of Taylor, we have to understand how these derivatives can operate on 2 vectors, 3 vectors, or k vectors. So, to make progress on answering this question, let's define what we mean by a bilinear map. Well, a bilinear map is just a mapping of 2 vectors to 1 vector that is linear in each argument. And there's 2 arguments, right? Because it's mapping 2 vectors to 1 vector. So if u, v, and w are vector spaces, and B maps a vector in U and a vector in V to a vector in W, in order for B to be a bilinear map, it means that B of a linear combination, alpha U1 plus beta U2, comma V, is equal to alpha B of U1, comma V plus beta B of U2, comma V. In other words, this linear operator can be distributed, right? The scalars can be factored out and the sum can be distributed. So if V is held constant, then I have a linear operator of the first argument. Similarly, if I hold U constant and let the second argument be a linear combination, then I can distribute. So it's linear with respect to the second argument as well. So this is a bilinear map. So let's take a look at an example. Consider a bilinear map that maps 2 vectors from Rn to a vector in R. Of course, a vector in R is just a number, defined by the bilinear map of B, U, comma V is V transpose AU, where A is a square n by n matrix. So that mapping is bilinear because it's, if V is kept constant, V transpose AU is linear with respect to the U argument, and if U is kept constant, V transpose AU is linear with respect to the V argument. That is, B of a linear combination alpha U1 plus beta U2, comma V is V transpose A times that linear combination. Of course, if V transpose is kept constant, I know that A times the linear combination can be distributed. That's a linear operation, right? That's just matrix vector multiplication, which is a linear operation. So I get the linear in the first argument criteria that I want. And of course, it's linear in the second argument too. If that first vector is replaced by a linear combination, alpha v1 plus beta v2 transpose, the transpose is linear. That linear combination of vectors times A is linear, and I get the linearity in the second argument property that I want. Now, a k-linear map is a mapping of k vectors to 1 vector. That is, this mapping is linear in each of the k different arguments. So, in one dimension, suppose f is differentiable on the open interval a to b. For each x naught in AB, f prime of x naught is a number. Now, a number in R is equivalent to a linear operator from R to R. The derivative f prime is a function of the interval a, b to R. Now remember, f prime of x naught is a number. For each x in a, b, f prime of x is a different number. And of course, that's the definition of a function. In multiple dimensions, if f is differentiable on an open subset of Rm, then for each x naught in the open domain, df of x naught is a linear operator from Rm to Rn, which of course can be represented by a matrix of size n by m. And if I'm differentiable on all of u, then for each x in u, I have a different linear map. So df maps every vector in u to a linear mapping from Rm to Rn. Now remember, the set of all linear maps from Rm to Rn is equivalent to all n by m size matrices. So I can think of df as a function that maps u to n by m matrices. In one dimension, if f prime, right, which is a function of the interval a to b, is differentiable at x naught, then its derivative is the second derivative of f, right? The first derivative of the first derivative is the second derivative of the original function. In multiple dimensions, if the function from u, which is in Rm, to matrices of size n by m is differentiable using my same definition of differentiability, if it's differentiable at x naught, what I mean is there exists a linear mapping from u and Rm to matrices in Rn by m. And of course, the second derivative of f is the derivative of the first derivative evaluated at x naught. The second derivative at a point, right? So the second derivative, when evaluated at a single point, is a linear map. Just like the second derivative of a calculus 1 style function at a point is a number. The second derivative of f at x naught at a single vector x naught is a linear map. It maps u in the domain, which is in Rm, to a matrix in Rn by m. In other words, the derivative at x naught maps u to a vector, to a matrix of size n by m. So if this object here is a matrix of size n by m, then I should be able to multiply it by a vector v in Rm, and that'll give me a vector in Rn. And all of these mappings, right, mapping of u, the mapping of v, these are all linear mappings. Because they're linear in the u and v argument, I have a bilinear map. Right? I can define this operation as some bilinear map h, which of course depends on x naught. It depends on where we're evaluating the second derivative. Right? Some h x naught of uv, and this is bilinear with respect to u and v because it represents two linear mappings. So h takes a vector in Rm and another vector in Rm and maps it to a vector in Rn. Now note the set of linear maps from Rm by Rm to Rn is equivalent to all n by m matrices, three-dimensional matrices. You might also call these tensors. Again, given a basis for my space. So what does this second derivative look like? Well, let's just suppose n is 1. If n is 1, in other words, the dimension of the codomain of f, the output of f, then the bilinear map h, right, which is of course indexed by x naught, where I'm evaluating the second derivative, that bilinear map maps a vector in Rm and another vector in Rm to R. So suppose I have a basis for Rm, u1, u2 through um. And u and v are m-dimensional vectors, or vectors in Rm. So I can write them as a linear combination of these basis vectors, where alpha are the coefficients of u and beta are the coefficients of v. So if I evaluate h at u comma v using this basis expansion, then I get the sum from k equals 1 through m and the sum from j equals 1 to m of alpha k, beta j, h evaluated at the basis functions. Well, in fact, that's just alpha transpose mh times beta, where mh is a matrix. Specifically, that matrix. In other words, if I have a basis for Rm, then I can represent the bilinear map as a matrix that operates on uv by taking the coefficient of one of the vectors, forming it into a vector called alpha, the coefficient of the other argument, call those coefficients beta, and taking this linear algebra operation, a matrix vector product, and then essentially a dot product. And this matrix can be computed by applying my second derivative evaluated at x naught times my basis vectors. So if f is real valued, in other words n is 1, the second derivative can be represented by a m by m matrix, where the bilinear map is represented by alpha transpose this m matrix that represents the bilinear map h times beta, given a basis for Rm, and the vector of coefficients alpha and beta. Now, what does this look like in the canonical basis, the basis that we're most likely to use, for one, and two, how do we actually compute this? Well, we compute it using the Hessian. If f maps an open subset of Rm to R is twice differentiable on this open set, then the matrix representation of the bilinear map with respect to the canonical basis of Rm is given by this matrix of second derivatives. And that matrix's second derivatives is called the Hessian matrix. Now, given certain conditions on the differentiability of f and the continuity of those derivatives, the Hessian can be symmetric. So here's the result, the symmetry of mixed partial derivatives. If f maps an open subset of Rm to Rn is twice differentiable, so just like the hypothesis of the Hessian theorem, and the second derivative function is continuous, so that's an extra condition that we didn't have in the Hessian theorem, that the second derivative is continuous. Of course, we know the first derivative is continuous because it's differentiable. The second derivative may not be differentiable, but it does have to be continuous. Then for each x in my domain, whether I take the derivative with respect to xj first and then xi, or xi first and then xj, I get the same result. Meaning that if this were true, then my Hessian matrix would be symmetric, of course, presuming that n is 1. By the way, what do I mean Rn by m by m? Well, I mean the set of all linear maps from Rm to Rn by m. Rm, because the domain U is in Rm, and the outcome of the second derivative, is the same thing as the outcome of a first derivative, which would be a n by m matrix. So we won't go through the proof of this in detail, but the idea is fairly straightforward given our previous result of the mean value theorem. Suppose I have some point x1, x2 in two-dimensional space. Here we're in the ith coordinate and the jth coordinate, so we might as well make that ith and jth coordinate 1 and 2. So we evaluate at that point. We take some perturbation in the x1 direction, some perturbation in the x2 direction to get a rectangle. And if I take the difference first in the perturbation direction of the x2 coordinate, the second coordinate, and then take the difference along the first coordinate, right? That's equivalent to the derivative with respect to x2 and then the derivative with respect to x1 at some point in my rectangle according to the mean value theorem. Right, if I take those differences divided by the size of the perturbation. Similarly, I could take my difference, my finite difference, first in the first coordinate, and then take the finite difference in the second coordinate second. Well, that's equivalent to the partial derivative with respect to x1 first, and then the partial derivative with respect to x2 at some coordinate inside the rectangle, again, by the mean value theorem. Now, if I take the limit as h and L go to 0, then if my second derivative is continuous, right, because I'm applying the mean value theorem twice, so if my second derivative is continuous, then the second derivative at C and D and the second derivative at C prime and D prime are going to converge to the same evaluation point at x1, x2. And that's how I can show that it doesn't matter what order I take my derivative, so long as that second derivative is continuous. So for the sake of completeness, here's a sketch of that proof, but essentially it's two applications of the mean value theorem, first in the second coordinate, then in the first coordinate, and then again in the first coordinate, then the second coordinate, and showing that as you take the limit of your perturbations, you end up with the same thing, given the continuity requirement. So the proof is there if you want to pause it and study it, but we've covered the idea. So that gives us a pretty thorough idea of what the second derivative looks like, but okay, what do the rest of the derivatives look like? Well, let's consider, again, a function that is real valued, that maps vectors in Rn to R. Well, the first derivative at x0 is a linear map from Rn to R, right? Again, just to review what we already know. And that's equivalent to a 1 by n matrix. Specifically, the derivative of f at x0 is the gradient transpose, right? So it's specifically that 1 by n matrix here. And if I apply my derivative to some u in Rn, then I get a linear map to a number, right? The derivative maps a vector in Rn linearly to a number in R. Again, the second derivative, which we just went over to review, the second derivative at x0 in u is a linear map from Rn to the value of the first derivative, which is a 1 by n matrix. Right? We could represent that as a 1 by n array, which of course we can represent as an n by n Hessian matrix. We can also think of it as a bilinear map that maps two vectors in Rn to a number in R. Right, so we know that the second derivative at x0 is equivalent to the Hessian matrix, which is a n by n matrix. So this bilinear map is equivalent to taking V transpose times the Hessian times Y, which of course gives me a number. The third derivative at x0 in u is a linear map from Rn to R1 by n, right, which is the form of the second derivative, which is equivalent to a 1 by n matrix, or what you might also call a tensor. Again, this is also equivalent to a trilinear map that maps three vectors from Rn to a number R. So the third derivative at x0 can be represented by a tensor in Rn by n. Right, we can drop the 1 just like these column vectors are often just described as vectors in Rn. Right, we can drop the 1, but it's a matrix of this size or a tensor of this size. And this tensor, when operating on three different vectors, returns a number in R. The jth derivative at x naught and u is a linear map from Rn to R1 by n by n by n by n. Of course, there are jn's there by 1. And again, the jth derivative can be thought of as a J-linear map that maps j n-dimensional vectors to a number R. Now, just for the sake of a simplified notation, if I have a j-tuple of the same vector h, for example, I'll write that as h to the j. Right. Again, consider where we're going. Right, we're going towards the Taylor polynomial for multidimensional functions. So, for example, if I apply the second derivative as a bilinear map to two vectors that are the same, h and h, I might write it as h to the parentheses 2, which is also h transpose times the Hessian times h. So, definition, a function is called a class CR if the first R derivatives exist and are continuous. Of course, all we really have to say is that the rth derivative is continuous, because if we're supposing differentiability over the entire domain, then of course each of those previous derivatives, if differentiable, are also continuous. So now we've come to the main event, Taylor's theorem. Suppose F maps an open subset of Rn to R is class CR plus 1 on U. And let the interval x naught to x, in other words, the set of all convex combinations of x naught and x, be contained in U. Then there exists a C in the open interval x naught to x. Remember, the open interval x naught to x is the set of all convex combinations of x naught and x, but not including x naught and x, for which f of x is f of x naught, right? X naught is kind of my point of tangency, plus the sum 1 over j factorial of the jth derivative of f at x naught times the j-tuple of the vector x minus x naught, plus my remainder term, right? And this is why I needed class C R plus 1, because my remainder term includes the r plus first derivative evaluated at some c in my convex combination interval. Now, the continuity of that r plus first derivative ensures that, right, my remainder term is small if x is near x naught. Specifically, that the limit as x goes to x naught of my remainder term divided by the difference of x minus x naught to the rth power is 0. So in other words, this goes to 0 faster than this does as x approaches x naught. Now the proof follows by successive applications of the mean value theorem. So we can prove it by induction. Let's consider the base case that r is 0. Well, the mean value theorem implies that f of x minus f of x naught equals the derivative at some c in the open interval x naught to x times x minus x naught. All right, so that's just a statement of the mean value theorem from the previous lecture. So that essentially gives us our result of a Taylor polynomial plus a remainder, and this is the remainder. Let's show that the remainder satisfies the convergence property. Of course, 0 is less than or equal to the absolute value of the remainder at some c times x minus x naught over the norm x minus x naught to the rth power. Of course, r here is 0, so to the 0th power, which means this is a denominator of 1. The derivative of f at c is the gradient transpose. So if I use the Schwartz, this is bounded by the norm of the gradient vector times the norm of the difference vector. And of course, the gradient of f at c is fixed, and as x approaches x naught, x minus x naught approaches 0, because that's what it means for x to approach x naught. So now let r equal 1. Now, of course, you might consider, well, we've already done the base case. Let's just go to the induction step. But let's do r equals 1 so we can get an idea of how the dynamics play out. Again, let's remember that the derivative of f evaluated at x naught times a vector h is the gradient of f at x naught transpose h. And the second derivative applied to the two-tuple h is just h transpose times the Hessian times h. So f of x naught plus h minus f of x naught is the integral from 0 to 1 of the derivative of f of x naught plus th. Right, so that's just an application of the fundamental theorem of calculus. Now we use the chain rule to compute that derivative. Right, because this is a function of a vector valued function of a number t. So we would use chain rule. We get the derivative of f at x naught plus th times the derivative of x naught plus th with respect to t, which would be the vector h. Right, then we could just use a bit of a trick here that the derivative of t minus 1 is 1. But by setting it up this way, it allows us to use some integration by parts. Where we're going to integrate by parts to get those higher order terms that we want to get to. So now we get that the difference is equal to the derivative of f at x naught plus th times h times t minus 1 evaluated from 0 to 1, from t equals 0 to t equals 1, minus this term, right? So this is just using the integration by parts formula. We evaluate. Now to take the next step, we need to remind ourselves of the generalized mean value theorem for definite integrals, which says if f is continuous, and by the way, our functions here are continuous, and g is continuous and non-negative. By the way, the role of g is played by 1 minus t, and we can see it's non-negative in this interval. Then there's a value of c for which the definite integral of f of t times g of t is f of c, right, for some c in the interval times the integral of g. So we're going to apply this result to this here. Again, this is g, and this entire thing is my f. So here's my result. I'm using some theta in 0, 1 instead of c and ab, right? Theta in 0, 1. The second derivative of f at x naught plus theta h. We'll call this whole thing some c in order to get it to look like the remainder term that we want, times the two-tuple of h times this integral, which is just 1/2. So rearranging gives f of x naught plus h equals my first order Taylor polynomial plus my remainder term. Right, that's exactly what I got at the bottom of the slide. If I just take this and add it to the other side, call this c, evaluate this integral, I get precisely this. So I get the right structure, my first order Taylor polynomial, I get the right structure of my remainder term. Does the remainder term behave as h goes to 0, right? That's also part of the theorem, is this convergence result of the remainder term. Well, of course, 0 is less than or equal to the absolute value of that remainder term divided by the norm of h to the r. Now remember, h is x minus x naught. Of course, the second derivative applied to the two-tuple of the vector h is just h transpose times a Hessian matrix times h, right? Right, this has a specific meaning for the structure of matrix we have, and it's specifically this: the vector transpose times my Hessian matrix times h. And that's less than or equal to the norm of the matrix times the norm of h squared, right? And that comes from using the definition of what a norm of a matrix means, and of course the Cauchy-Schwarz. Now, the norm of h squared divided by the norm of h, the norm of h cancels, and of course that term goes to 0 as h goes to 0. Now remember, h is x minus x naught, so as x goes to 0, x approaches x naught. And so that's precisely the convergence result that I need for my remainder term to say that when r equals 1, Taylor is true. Now suppose Taylor is true at r equal to k minus 1. Well, if Taylor is true for r equal to k minus 1, then I have exactly this setup where this red term is my remainder. So my goal is to show that this remainder term can be written as the kth term of my Taylor polynomial plus my higher order remainder term, right? Higher order by 1. Right? If I can show that this old remainder equals the kth Taylor term plus a new higher order remainder, then I've shown Taylor theorem is true at r equals to k, which would complete my induction proof. Of course, I have to show that this new higher order remainder term behaves, in other words, converges at the correct rate. So again, let h be x minus x naught, and let's consider that remainder term. Now this 1 over k factorial can be written as 1 over k times k minus 1 factorial, and notice I'm expressing 1 divided by k very creatively. So this equality follows by again applying the generalized mean value theorem. Integration by parts will get me this new term, and the mean value theorem will get me this term. So I've achieved my result so long as this new remainder term converges at the correct rate. So let's consider. Now, you may look at this and say, well, what do you mean by the norm of d to the k plus 1 of c? Well, d to the k plus 1 of c is we could think of it as a k-linear operator, or a operator that maps k vectors linearly in each argument. So when I say the norm of this operation, what I mean is the induced norm on an operator, which is to say the max value the operator takes when it operates on a unit vector. And that's why I can get this inequality. Because of course I'm operating on k plus 1 vectors. Divided by the norm of h to the kth power, my k and my k plus 1 cancel. Because my denominator cancels, this goes to 0 as h goes to 0. Which is to say that x converges to x naught. And so that completes the proof. Now, it's not crucial that every single step of this proof you could recreate at a moment's notice. Not for this class. It's not crucial that the proof is right now completely crystal clear, but the ideas should be clear. The idea of using the mean value theorem to show that or to relate a difference and a derivative at some point on the interval of the difference. Right, this relationship between differences and derivatives using the mean value theorem, that idea should make sense. Of course, knowing how to integrate by parts and the generalized mean value theorem for definite integrals, these are all concepts that should make sense. And the idea, the flavor, right, of this proof should make sense. But right, it's not crucial that you could recreate this at a moment's notice, but you should be able to follow the ideas. Of course, what we should be able to do is, given a function, we should be able to compute a Taylor expansion. And we should even be able to describe how close that Taylor expansion is to my original function, at least in the limit as where I'm evaluating x converges to x naught, my point of expansion. So let's take a look at an example. Let's consider the function f of x as 3 e to the 2x1 times cosine of 4x2 minus x1 x2. So let's give the second order Taylor polynomial to f at x naught. Right, so let's take a look. Notice f of x, right? Well, x has a x1 component and an x2 component. So f maps vectors in R2 to numbers, right? F is real valued. So if I want a second order Taylor polynomial, I need a first derivative, that's a gradient transpose. I need a second derivative, that's a Hessian matrix. So here's my recipe, right? The recipe for Taylor says it's equal to f of 0 plus the derivative of f evaluated at 0 times x plus the second derivative of f at 0 times the 2 tuple of x. And of course that literally means f of 0 plus the gradient of f at 0 transpose x plus x transpose the Hessian of f evaluated at 0 times x. So there's my recipe. Well, I need my ingredients. The derivative, it's the gradient transpose, which is the vector whose first entry is the derivative of f with respect to x1, and then the derivative of f with respect to x2. So the derivative of f with respect to x1, of course we could go through and take that partial derivative, right? It's just a calculus review. Same thing for the second derivative. We get that vector, of course, transpose, right? Because we get a row vector, right? The derivative has to be of size 1 by 2. When I evaluate it at 0, I'm going to get 6 times e to the 0 times cosine of 0 minus 0, 6. And negative 12 times e to the 0 times sine of 0 minus 0, which is 0. So there's my derivative when I evaluate at 0. I get the vector 6, 0. Or I can think of it as the 1 by 2 matrix 6, 0. Now the Hessian matrix is a 2 by 2 matrix given by those partial derivatives. And the Hessian matrix is given by a 2 by 2 matrix of second partial derivatives, second order partial derivatives. And of course we could go through and take those partial derivatives. Notice that f is not only twice differentiable, but the second derivative is going to be, all of the second derivatives are each continuous, which means my Hessian matrix is symmetric. And of course we can see that there, that my Hessian matrix is symmetric. That is, the 1, 2 entry and the 2, 1 entry are equal. In other words, if I take this derivative with respect to x2 and this derivative with respect to x1, I will end up with the same outcome, this or this, because they're the same. And when I evaluate at 0, I get my Hessian evaluated at 0, which would be 12, negative 1, negative 1, negative 48. And of course, that's the matrix that's going to define my bilinear map, specifically given by this term. So I now have all the ingredients, so I can add my ingredients to the recipe. And my second order Taylor polynomial is given by this polynomial. 3 plus the vector 6, 0 transpose x plus x transpose times the matrix 12, negative 1, negative 1, negative 48, x. Right, so this is a quadratic, right, or a second order polynomial of vectors in R2 to numbers R. Furthermore, the difference of f and t2 divided by the norm of x squared is 0. That's given to us, that's guaranteed to us by the Taylor theorem. That's all for today.